Hi, Rachel!
Hi, Linggit!
So, mga musta kayo sa buong? How are you today? Batian ko, broken.
Hindi na pagsuryahan.
Wag.
Wag na muna nating pag-usapan.
So, welcome to the Nature of Reality, where we explore the fundamental questions about the universe and our place in it. Once again, I'm Lincoln.
And I am Rachel. Today, we're diving into Ian Stewart's Nature's Numbers, specifically Chapter 4, and grappling with the core tension: is the universe governed by fixed laws, or is it all a constant, unpredictable flux?
Exactly. Stewart points out that the nature rather, presents us with two seemingly opposing views. One is a universe of fixed, immutable laws, and the other is reality of constant change with no objective truth.
And it's Isaac Newton who really steps in and changes the game. He represents the triumph of rationality over mysticism, showing us that these two views are not mutually exclusive.
Right. Stewart says, the universe may appear to be storm-tossed ocean of change, but Newton, and before him, Galileo and Kepler, realized that change obeys rules. Not only can law and flux coexist, but law generates flux.
Before Newton, mathematics offered a largely static view of nature. Think about Ptolemy's theory of planetary motion, with its complex system of epicycles and deferents.
Yeah, Ptolemy tried to explain planetary motion using a series of circles within circles, partner, which was incredibly complicated. It was a static model, trying to fit observations to preconceived idea of a perfect circular motion.
Then, Kepler comes along and challenges that, showing that planets move in ellipses, not perfect circles. And, and Newton takes a step further, replacing those static forms with the dynamic laws that produce them.
He does this by looking at something as simple as cannonball's trajectory. He understood, thanks to Galileo, that the path of projectile is parabola.
But Newton's key insight was that while the position of the cannonball changes in a complex way, its velocity changes more simply, and its acceleration is constant.
Let's break down calculus in a nutshell here. We have three mathematical patterns: height, velocity, and acceleration. Calculus, specifically differentiation, allows us to move between these. If we know one, we can figure out the others.
And the question becomes, why is the acceleration fixed when everything else is in flux? Newton's answer has two parts. The gravity pulls the ball downward, and a constant force produces a constant acceleration. This leads to his famous law: force equals mass times acceleration.
And calculus is a mathematical tool Newton invented to handle these rates of change. It's a way to bridge the gap between observed behavior and underlying laws.
Stewart makes a great point. Newton's law of motion teaches an important lesson, namely, that the route from the nature's law to nature's behavior need to be direct and not obvious. Between the behavior we observe and the laws that produce, it is a crevasse which the human mind can bridge only by mathematical calculations.
He emphasizes that mathematics is a powerful tool for understanding nature's patterns, even if it doesn't mean nature is mathematics.
And this approach, using differential equations to describe rates of change, becomes the foundation for much of physics. We see it in the heat, the wave equation, and the laws governing light, sound, and fluids.
But as science advanced, the meaning of solved evolved. Initially, it meant finding a precise formula. Newton himself did this with gravity, showing that the force between two bodies follows an inverse square law and leads to elliptical orbits.
However, when they tried to extend these three or more bodies, like the moon, earth, sun system, they hit a wall. The three-body problem proved for more complex.
And this is where we see the meaning of solve change. From finding formulas to finding approximate numbers, like Delaunay's 20-year effort to calculate the moon's motion.
And then, with the work of Vladimir Arnold and Ji Hong Sha, we realized that three-body problem isn't integrable, and it can exhibit chaotic behavior like Arnold diffusion.
So, solve the shift again. To tell me what the solutions look like, focusing on qualitative aspects rather than precise formulas.
We can recognize that some systems are inherently complex, and formulas can't capture their full behavior. This shift towards qualitative analysis is a major advance.
It's about understanding nature's patterns in their own terms, not forcing them into preconceived mathematical mold.
So, Newton's revolution wasn't just about discovering laws. It was about changing how we approach those laws, from static forms to dynamic processes.
And it showed us that law and flux can coexist, and mathematics is the bridge between them.
We've seen how Newton's initial insight into calculus and motion laid the groundwork for understanding change in the universe. But we've also seen how the limitation of those initial approaches, particularly with a complex system like the three-body problem, force mathematicians and physicists to rethink what it means to solve a problem.
Exactly. We move from seeking precise formulas to accepting approximations and ultimately to understanding the qualitative behavior of systems. This evolution reflects a deeper understanding of nature itself. That it's not always about finding exact solutions, but about grasping the underlying patterns and dynamics.
In essence, this chapter highlights the power of mathematical thinking to bridge the gap between our observation and the hidden workings of the universe. It demonstrates how our understanding of nature evolves as we develop new mathematical tools and approaches.
And it reminds us that the quest for knowledge is not always a linear path. Sometimes, the most significant breakthroughs come from acknowledging the limits of our current methods and embracing the new ways of thinking.
Ultimately, Newton's legacy is not just about the laws he discovered, but about the
Paradigm partner,
paradigm shift he initiated, a shift that continued to shape our understanding of reality.
thanks for joining us on the nature of reality.
We hope you gain a new perspective on how we understand the universe.
Thank you and goodbye.